Good evening, everyone. My name is Sai Aditya Pradeep, and I'm the Scientific Program Manager for the Artificially Intelligent Manufacturing Paradigm for Composites. As part of our EFRC Center, we are here for the AIM webinar series. Before we get into the webinar, I would like to talk a little bit about the EFRC Center. Our center is located at over 8 different locations in the contiguous United States, with Clemson University, University of Delaware, South Carolina State University, University of Florida, the Ohio State University, and Brown University being the primary university participants, as well as 2 different national labs, Pacific Northwest National Lab, as well as Savannah River National Lab. Our particular EFRC has a mission to build an AI-enabled inverse design approach in order to fundamentally understand and integrate material, manufacturing, design of advanced polymer composites. While uncovering these fundamental insights, our EFRC also aims to build an inverse design software tool. We hope that this would accelerate the discovery of advanced polymer composites for improved performance and energy-efficient manufacturing, thereby enabling a smaller carbon footprint, lower structural weight, and lower cost. This particular webinar series is in its season 2, where we focus on imparting 21st century skills as identified by the National Academies Press. These skills include critical thinking, problem solving, analysis, reasoning, decision making, adaptive learning, information literacy, oral and written communication, and active listening. All of these are essential for navigating the complexities of today's research and development landscape. This series features talks focused on several different career paths ranging from national labs, industry, and consulting. And with that, I would like to request the director of this AIM EFRC, Dr. Srikanth Pilla, to introduce our guest speaker for today.
Thank you, Sai. Welcome, everyone, once again. It's my pleasure to introduce today's speaker, Dr. Chris Curry. Dr. Curry received his undergrad as well as doctoral degree in polymer science and engineering from the University of Southern Mississippi in 95 and 2000, respectively. For many of you who are probably in the polymers and composites field, as you may know, that USM is one of the top premier programs in polymers in the country. So, following his graduation, he began his career as a research scientist in ExxonMobil, and over the past 24 years, he held various different positions, escalating within the company and taking on many different roles. And today, he is a senior advisor in ExxonMobil's Technology Scouting and Ventures Group. And we had a very chance meeting actually a few weeks ago as part of a bigger, larger strategical partnership we are trying to build. And when I heard about Chris and his background and his enthusiasm outside his technical field, and what he does, I invited him to share his thoughts and experiences with our team, and he graciously agreed. So I'm so thankful for his willingness to share his journey and story. So with that, I'll let Sai do rest of the introduction.
All right. Thank you, Dr. Pilla. Just before we get into the talk, I would just like to acknowledge that this webinar is brought to you by the AIM for Composites Energy Frontier Research Center, which is sponsored by the Department of Energy, specifically the Office of Science, under this particular award. We have recurring webinars every month, and for information for any of these webinars, please do check out our social media, our YouTube channel and LinkedIn page. Our next speaker is Dr. Ryan Hanlon, and he will be talking about career paths in industrial R&D. This would be on December 16th, and this information will go out to all our social media channels pretty soon. So with that, I would like to request Dr. Chris Curry to take the stage. And
well, thank you for the introduction, and thank you for the opportunity to speak to this group. I'm calling you from Baytown, Texas right now, which happens to house ExxonMobil Technology and Engineering's, I'd say, second largest technology site in the United States. And I'll tell everybody up front that this is not a deep technical talk. Instead, it is a very condensed summary of my career journey, starting from graduate school through my time here at ExxonMobil, that sprinkles in some technical aspects to illustrate some of the lessons that I've learned over the past 29 years about innovation. The few slides that I will present, they were actually created with a student audience in mind. In fact, they were created for myself back as a student in 1996. At that time, I had finished my bachelor's in polymer science. I'd finished my first year of graduate studies and passed my cumulative exams, then put me on the path for about 4 years of research to attain my doctorate. At that time, my career ambition was to go into academia, to teach students and to lead a research group. At that time, I had this sincere passion, deep passion for creating new materials. I'm a synthetic polymer chemist by trade, and I thought that the only way to continue innovating was to remain in academia, dreaming up new polymer architectures and crazy new ways to put them together. It would be fascinating if I could go back and give myself this presentation in 1996 to illustrate actually how innovation occurs and how much of it actually happens outside of a fume hood or a dry box. So since I can't go back in time, I'm hoping that for those of you who have a passion for creating things, that sharing my story will provide you with some examples of the unexpected ways in which you can satisfy that passion. So let's get started. Again, it's not a technical talk, but this first slide might scare you a little bit. So here I am, beginning my research thesis back in 1996, and my professor and I had dreamed up what is my research project going to be for the next 3 or 4 years. And here it is on a slide. I was really big in living carbocationic polymerization, particularly of polyisobutylene, polystyrene vinyl ethers. And the next 3 years are going to be very, very easy. We were going to take a difunctional initiator and a dicumyl chloride. We were going to polymerize with isobutylene at -80 degrees Celsius with a Lewis acid, and parts per million of an additive that was known to turn these polymerizations into living systems. Once the polymerization is complete, it was known in the literature that you could add allyl trimethylsilane. It was a quantitative reaction that would produce a telecalic polymer with allyl groups on the ends. After cleanup, then the subsequent reaction, hydrosylation reaction with triethoxysilane using a hexachloroplatinic acid, then would put these triethoxysilyl groups, telecalic, which I've shown here is sort of a cartoon instead of continuing to draw the stick structures. And then react it with a stoichiometric amount of living polystyrene in order to get these fancy styrene, isobutylene, styrene triblock copolymers, where the diethoxysilyl groups were attached at the block junctures. All right, now that's as technical as this slide gets. So why were we doing this? Well, there was a hypothesis that my professor had, along with a research grant from the Department of Defense, that these materials, and hold on, let me get my pointer real quick. These materials could serve as an interesting product to make garments for chemical warfare. So the soldiers would put on these garments, and these are like rubber-like materials. And then when it cools, it would have a rubbery type of performance because of the polyisobutylene. But then the phase segregation of the polystyrene blocks would then make it look like it was cross-linked, but it was really thermally reversible cross-links. And at the juncture, you would have these triethoxysilyl groups. The hydrophobic nature of the polystyrene and the polyisobutylene would thwart any of the chemical warfare agents that would come, whereas right around the block junctures, you would have these hydrophilic groups that would then subsequently be cured that would allow wicking of perspiration from the soldier. All right, so I said, okay, this is easy. Give me about 3 or 4 months, I'll have this thing licked out, and then we'll do a lot of characterization, and I'll write my papers, and I'll get out. Well, 9 months later, I still could not make this first precursor. And because it turned out that this reaction was not quantitative. And we could not understand why. So then, my job was not really to understand the fundamentals of this polymerization, the mechanisms of this polymerization. It was to use this method to create materials. Well, because I could not make this, it forced me to go back and understand this. So it was known about 10 years at that time that the addition of small concentrations of these electrophiles in this system produced a living polymerization. So if you do not have them, then you would get very broad polydispersity materials, kind of runaway polymerization kinetics, and lots of chain transfer and chain termination. But when you added just small amounts of this, then it turned it into a living system. So I had to spend my time, instead of making these glycopolymers, understanding what was going on in order to make these polymers. Well, 4 years later, after studying this, I ended up publishing 3 papers, my dissertation. I got a Best Poster Award at a American Chemical Society meeting. And it turned out to be probably, I think, well, my advisor told me some of the best work that his group put out in the 39 years that he taught. These are actual slides from my dissertation that I delivered, as you can see, October 26th of 2000, so almost exactly a little over 24 years ago. And what it was a deep understanding of the limits of livingness of this carbocationic polymerization system. And why do we add those electron donors? Effectively what they did is they created a common ion salt, which then suppressed the formation of free ions, which was really the culprit that led to non-living conditions. It also, we were able to understand, chain end degradation during this polymerization mechanism. We did some kinetics of that chain end depletion. We were able to do a lot of structural analysis of different types of coupling mechanisms that were supposedly not supposed to happen, but that do happen under certain conditions. And then we posited a synthetic pathway for the coupling that occurs and how to rid the system of it. So effectively, it had what had started out as being a project to make certain types of materials ended up being work that defined for the entire carbocationic polymerization community the guardrails of livingness for this system. So I go through all that to kind of point out the first lesson that I will share today, and that is don't ignore serendipity. I can say since that time, in the subsequent 24 years of working at ExxonMobil, I've had this happen to me probably 3 to 5 other times where we start a project and we get a year into a project and it's just not going as it was planned, and then we had to pivot. So I'm telling all of you out there is that when you start to get those signals that things aren't going to work, don't stop. Just start looking in a different direction, because it could be luck that's trying to point you in a better path. So I finished my PhD in October of 2000, and then subsequently I joined ExxonMobil in Baton Rouge, Louisiana. At that time, we had a small group there that was doing adhesion technology, essentially making molecules for the hot melt adhesive industry. And then that led me to start working on a whole variety of different types of molecules, and I'll point them out here. You'll notice that the majority of them do not contain heteroatoms. ExxonMobil is allergic to heteroatoms like oxygen and nitrogen. That's a joke. But throughout my career, at least the first 5, 6 years of my career, I had the luxury of working on a myriad of different types of polyolefinic types of materials. So I'll start here. This is butyl rubber. These are, well, you can't see it, but it's ethylene, propylene copolymers. We usually make them with metallocene catalysis. These are an interesting class of materials called thermoplastic vulcanates. So in most cases, the continuous matrix is polypropylene, whereas the discontinuous matrix is a cured rubber. And these behave like a cross-linked rubber system, but yet they behave like, or they process like thermoplastics. Different copolymers of ethylene with, in this case, vinyl acetate, but different acrylates. Block copolymers again, but in this case, I worked with a joint venture that we once had with Dow, using living anionic polymerization to make craton-like materials, where the end blocks were polystyrene, the mid blocks were polyisoprene or polybutadiene. And on a commercial scale, we were able to make all sorts of different architectures, and I've shown here too, tri-blocks and stars. That was amazing to see a living carboanionic polymerization done at scale, where, you know, just molecules of water within a huge reactor can cause an upset. This is ethylene propylene diene monomer material, EPDMs. But where I started was in this category here. So these are oligomers, actually. Oligomers of dicyclopentadiene and oligomers of 1,3-pentadiene. And these are actually used quite often in making hot melt adhesives. So think tapes, labels, think of things that close your cereal boxes. And they got a very interesting start in that a long time ago, these were considered sort of trash molecules at the byproducts, unwanted byproducts in steam cracking process. You know, steam crackers, they're designed to maximize the production of ethylene and propylene, but you inevitably get some higher carbon number materials that you've got to find some disposition for. And a long time ago, those higher carbon numbers, like dicyclopentadiene, like 1,3-pentadiene, were actually blended back into motor gasoline, which actually used to cause gumming of your engines. And then someone decided, hey, why don't we take that trash, instead of blending it back into motor gasoline, let's see if we can find a higher value disposition for them, and found out that they're actually very useful in creating adhesives. There are a class of materials that are called anti-plasticizers, in the fact that whenever they're very low molecular weight, like 1,000 grams per mole, and so whenever you blend them with a traditional higher molecular weight polymer, you reduce the viscosity of the blend, but you increase the glass transition temperature, because this molecule here has a T sub G, you know, somewhere in the 50 to 60 degrees Celsius. So extremely unique materials. So coming out of graduate school, as I discussed on the previous slide, I was a macromolecular engineer. And every time I worked with a different type of system, my brain immediately went to, wow, what if I put an acrylic acid functionality here? Or what if I turn this into a block structure? Or what if I put a long chain branch here? I was always thinking of creating that really, really, really cool, you know, architecture, you know, solving that synthetic challenge. And I remember, you know, after about a year in, my boss at the time, who was also extremely technical and ended up being a long-term career mentor of mine, he sat me down and he said, Chris, obviously you're very creative, you're thinking outside the box, you're trying to come up with some new molecules, but in the end, we're a for-profit company. And if you're going to make something, then you've got to be somewhat convinced that it is of value to a marketplace, that it is solving a technical challenge for a customer and a customer of their customer. So as you start to think about different ways to make stuff, always start with the market and a potential problem to solve, and then go backwards to being a creative synthetic chemist, which was extremely valuable, because after that first year, I was taken out of the lab and I went out into the marketplace. And so I was still in technology, but I was working with customers, not only all around the United States, but also all around the world. And in some cases, I was working with their customers. For example, I'll start in the top left. going to the adhesion story I was telling you, we would sell these types of molecules to a company like Hinkle, which I think a lot of you probably are aware of. They are one of the world's largest producer of adhesives, and they would then blend these with other molecules to create an adhesive that would then be used to put together a diaper. A lot of people don't know that today's diapers actually have around upwards to a half a gram of hot melt adhesive within them. And so I would work with Hinkle to create a material that they could then use to make the adhesive that then would go into a diaper. Then subsequently, I'd work with Hinkle and someone like a Procter & Gamble or Kimberly-Clark to make sure that the adhesive ran well on their diaper lines. Worked with 3M, for example, for different types of tapes, Cooper Automotive for belt for hoses and automobile applications, people who made asphalt type of products for roadways, as well as major suppliers of paints that are used to create the lines on these roads. OEMs who manufacture parts for automobile manufacturers. This is a glass run channel that uses things like this thermoplastic vulcanate and EPDM that I mentioned. Wire sheathing. This is another spray adhesive application. So what you can see here are these filaments that are spraying. Carpet backing applications, oriented polypropylene films, photovoltaics. I'll skip the tire for a moment. This is the cardboard box sealing that uses the same type of adhesive that kind of goes into a diaper. Roofing membranes. And then this tire application was a really interesting one. We worked with a company called Yokohama, where we were trying to displace the inner liner of a tire with more of a nylon rubber plastic vulcanate that would have even higher retention than the incumbent material. So, I've got to work with a lot of different markets, with a lot of different customers in a lot of different regions of the world. And after doing that for, probably 6 years of my career, after I started with ExxonMobil, the words of wisdom that my first boss gave me really, really rang true, which is you can make something really neat and you can create something really fantastic. But if it doesn't really solve a need, if it doesn't address a problem, if there's not value for someone, then you're sort of wasting your time. So that's my second piece of advice for all of you out there. So after I finished working in the technology space, or after about 6 years of working in the technology area for ExxonMobil, I was convinced, and I mean that literally, convinced to get outside of the technology ecosystem within ExxonMobil and try something new. Specifically, I was being asked to go into sales. And I resisted that. I thought to myself, I'm having fun. I'm adding value. This is what I'm trained to do. I have, 2 degrees in polymer science. Why would I ever consider getting outside of technology to do something different? And I was convinced. I was convinced by the vice president of one of the businesses that I worked for to take a leap. Just try something out. And if you don't like it, okay, great. Then you can go back into technology. And so he convinced me. And I'll give you that story and start that story in just a moment. But I do want to tell you, it's very interesting that vice president, for one of the smallest businesses that ExxonMobil Chemical had at the time, was Darren Woods, who is currently the CEO of the entire corporation. And so the few times that I've seen him since, I've thanked him for actually pushing me out the window and encouraging me to try something new. So I'd say one of the reasons why I was a little concerned was that, A, it was outside of my comfort zone, but B, I wanted to continue to create. I wanted to continue to innovate, and I just didn't think that you could do that outside the lab. But for the next, I would say, probably 14 years, I found that was not the case. So some examples. So I went into sales, and I can tell you that it's hard to match the creativity and the innovation that you have to display when you're coming up with a $50 million contract with a global customer where you're negotiating on terms. They want everything, ExxonMobil wants everything, and then trying to find a creative way for both parties to have a win-win. Then, of course, you got a contract, then you got to supply them. Well, you got to find creative ways to supply them that product. Do they need it in pellets? Do they need it in bales? Do they need it in drums? Do they need it in boxes? Do they need it in bags? Do they need it in conditioned warehouses or in rail cars or in silos? Trying to piece together that puzzle where it's beneficial for ExxonMobil in a form to supply something to a customer that's beneficial for their operations. And in many of the customers I worked with, they also had non-US affiliates. And so, there was no worse call than I would get from a customer or their procurement agent here in the United States saying, our affiliate down in Brazil needs 20 tons of material within 10 days or they shut down their operations, which will affect Procter & Gamble, for example. Then trying to find, working with supply chain colleagues to try to find creative ways to get those containers onto the next shipment that goes down from Houston to Buenos Aires or to Rio. So after I did sales for a while, then I went into a business strategy where I did strategy work for 3 different business units over a span of about four years. And I was kind of excited because it gave me the opportunity to kind of get back into technology a little bit. So for example, the first strategy I worked on, this is a cartoon schematic of a gas phase polyethylene reactor. A real picture can be shown down here at the bottom. And the strategy was this. There are 3 main components that are used to make gas phase polyethylene. You've got silica support. You have a catalyst, a metallocene catalyst or a ziegler-natta catalyst that's supported on that silica. And then you ultimately have an activator that turns on the catalyst and begins the polymerization. We didn't know it at the time, but we had found ourselves in the position where these 3 main components for our chemical business's largest business, polyethylene, was being sourced by or from one particular supplier. So the growth plans for ExxonMobil Chemical, which at the time was probably the 2nd largest chemical company in the world, for their biggest business, it was all being controlled really by one supplier because they supplied us the majority of these 3 components. So my strategy was more of a supply diversification strategy. And that led to a lot of creativity in understanding how can you convince other potential suppliers to build multi-million-dollar assets to supply us with more catalyst or more activator or more support. I've led another strategy that was looking at putting together a 5 to 10 year plan for another one of our business units that was not doing so well. And in order to come up with the strategy, you've got to understand first what is happening in the world outside of your business. You can't just develop a strategy by looking within your own 4 walls. In order to do that, you've got to come up with some very creative assumptions about, okay, what is the supply demand dynamics for these particular products going out 5 years, 10 years, 20 years, 40 years? What is the competitiveness of our assets relative to our competitors' assets? And so that's what I've shown here is just some simple graphs that nobody's going to give you this data, and you have to spend months triangulating this information through various conversations and reports and market studies to understand, okay, well, for example, here's the current price back in 2013. You see the price starts to drop, the demand in different regions, and then how much supply is going to come on. Here's what's called a supply curve. Where you've plotted, your assets relative to all of your competitors' assets and stack them up to see which one is the least competitive, i.e. the highest cost to manufacture, and which one is the most competitive. And then using, these two types of information, then you can come up with like I said, a 5 to 10 year strategy about, well, what can our business do that addresses the supply demand dynamics going forward, as well as our competitiveness or non-competitiveness in terms of our assets. And then here are some pictures just to kind of illustrate that. I mentioned this is a gas phase polyethylene reactor, and this is actually blown film. So this is how we make a lot of, the industry makes a lot of polyethylene packaging film, which was another piece of work that I did whenever I became the polyethylene technology manager. So another example of not being in the lab, but having to be really creative and really innovative to put together some really important strategies for our businesses. One of the most recent pieces of work that I did was I led a study for about a year looking at the physical footprint of ExxonMobil's technology locations all across North America. So we currently have technical facilities in 2 locations in Canada. We have the facility that I'm at here now, and then we also have our facility in Clinton, New Jersey. And then after a year of studying, we proposed a strategy which would be a consolidation of many of these sites into the Houston area. So this is an example where it brought me back to technology, but I wasn't really in technology, and we had to find some really creative ways to make sure that we maintained the right capabilities for research for the ExxonMobil Corporation while trying to minimize at all cost attrition that would be expected as a result of closing and consolidating locations down into the Houston area. And the last one I'll share is from 2016 through 2018, I was in a position where I worked closely with our corporate strategic planning organization and the management committee itself, where we had to constantly share with an external audience, the things that we're doing in technology for the corporation, showing how, that work that we're doing provides us with a competitive advantage. And then finding a way to explain to the external world who are not scientists, why it's of value that we work in this place, why you should invest in us because of this competitive advantage. And what I've shown here is, this is me in 2017 at the annual shareholders meeting for ExxonMobil Corporation. And I was lucky enough to be given the opportunity to be the technology representative for the corporation. We had a booth here. What's interesting, you can't really see it, but this is like a little plexiglass stand with these cool little vials of different liquids and solids to illustrate, the products we're making and the catalysts that we use. Don't tell anybody, but it was just a mineral oil with some food dye in it. Also, I got involved in the development of our annual reports, where we have to show the value of technology delivery. And I would say this is probably the most rigorous publication that I've ever been involved in, even more so than creating my dissertation. You spend months helping the corporation put together the technical factoids that go into this. And then when it's all said and done, they fly everybody into Dallas, and then we had to sign that everything that's in there is truthful, just because it's so important to make sure that we're communicating with integrity to the external environment. Okay, so now, what am I doing now? Well, first, let me just sum it up. As I've tried to demonstrate through this slide, is that, after about 14 years of being outside the lab, I proved to myself that innovation can occur anywhere, and there are really, really challenging problems wherever you look. And I certainly had my fill of them throughout that portion of my career. So the last lesson is look outside, look around for better ideas. More than likely, somebody else has got a better way of doing something that you're trying to do. I'd say ExxonMobil for a long time, we've felt that, developing our technology internally is the best approach, and it has certainly been very successful for us for a very long time. That being said, we recognize, like the rest of the world, that innovation is democratized. and good ideas can come from anywhere around the world. And so instead of trying to create it yourselves, why don't we go look for it and incubate it and bring it in? If we can do that quickly, easily, cheaply, more efficiently. So I'm part of a group that's called Technology Scouting and Innovation, and it's a small group that is made up of experts that look for external technologies, startup companies, that span the needs of the entire corporation. So I have colleagues in my group that are looking for new ways for unconventional oil extraction, lithium extraction, capital projects, new ways to do that. My focus area is more on the downstream side of things, and I'll talk about that in just a moment. But what this does is looking outside, looking around, looking up for better ideas. How we do it is we scout universities, innovation hubs, venture capital firms, which is one of the reasons why I had met Dr. Pila, was because I wanted to learn more about what was going there on there at Delaware. Then we take these ideas, select ideas where we can see that there might be some potential value if it's scaled well, and we incubate them internally. So I find something, I incubate it with a potential owner of this technology within ExxonMobil to sort of semi-scale it up a little bit to see if we can really prove out that anticipated value. And then if we find that there's value, then it allows us to accelerate because then we can integrate it with our feeds, our assets, the competencies that we have within ExxonMobil, and alignment with particular business strategies and get them commercialized as fast as possible. The benefits to this, you can find new things if you look around, and it also can significantly increase your speed to market. The problem that we consistently face, and I think this is not just unique to ExxonMobil, but it's unique to anywhere there's innovation occurring, is that trying to avoid that not invented here mentality. Scientists forever have always said, well, I think I can do it better. I can create it better. I can invent it better. I can scale it up better. And trying to convince ourselves that in many cases, bringing in outside ideas, complementing with what you're doing is actually a better approach than just pursuing it all yourself. So what are the types of things that I look for? Well, we have 5 main areas that we look for the corporation. Growing or supporting the oil value chain, obviously, growing natural gas demand, reliability, finding new techniques, new sensors, AI to help increase the reliability and safety of our operations, capital projects. So ExxonMobil spends about $25 billion a year in building things around the world. And so any technologies or business models that we can find externally to help us just shave off 1% is a significant savings for the corporation. And then greenhouse gas, sustainability, circularity. So for me, the areas that I focus on whenever I'm looking externally, I've highlighted here in red. And I'll give you some examples of some of the things that I'm looking at. I'm not saying that we're doing them, but these are the kinds of things that I open my eyes toward whenever I see. So flow batteries. I'm not sure, I assume that all of you are familiar with flow batteries, electrochemical, redox batteries. I'm looking for any sort of novel materials where ExxonMobil might be able to play in these types of technologies. Also in some of the more traditional batteries. So here's a very simple schematic of a lithium-ion battery. And looking at the material design for anodes or cathodes, and then also understanding how is that technology evolving and where can ExxonMobil participate. Right now there's a lot of graphite that's used in the anode of lithium-ion batteries. We happen to make a lot of carbon, so we're looking into that space. But what happens if that anode starts to turn to silicon anodes? Are there other material plays for ExxonMobil? Another big area of research, and as well as many startup companies, is electrolysis. So electrolysis of CO2 with or without water to produce a myriad of different chemicals. I mean, I call it internally the CO2 plus electricity to X technology. And X can be methanol, it can be acetic acid, it could be formic acid, ethyl formate, sustainable aviation fuel, graphite. So looking for novel methods to produce chemicals of interest for ExxonMobil. This is a composite of one of our materials called Proxima, which is a polydisylcopentadiene. This is a glass fiber composite, which is a turbine outside of a wind turbine blade. Looking for any sort of novel composite type materials that ExxonMobil might be interested in. Forms of graphite, forms of carbon fibers, carbon nanotubes, graphene. And then lastly, in circularity. So we have a venture going on right now, our advanced recycling venture, which is taking used plastic and then doing advanced recycling processes to turn that plastic back into its original building blocks. And so I'm always on the lookout for opportunities to be able to complement that advanced recycling, or opportunities where we can take used plastic and where mixed use plastic and where we can do it efficiently, cost effectively, upgrade that used plastic into materials that consumers can reuse. So I hope this has been informative. Like I said, I wanted to kind of use my career experiences to tell some of the younger folks out there that as you begin your career, don't ignore serendipity and luck, because it has a big role to play in innovation. Innovation can occur anywhere, and it can be in non-technical assignments. Also, look around for better ideas, because more than likely they're outside and not necessarily within your own four walls. And I forgot my fourth one, but there's four in there. So I'm going to stop right now and open it up for any questions for the remainder time that we have.